Hello guys, um, this is gonna be your video for your laboratory number 9, which is gonna be techniques to determine concentration, and this is gonna be covering basically titration and spectrophotometry. So moving forward with this, I would like to discuss with you a few upcoming due dates. Remember that next Friday you have due homework 11 plus this laboratory report, and on next Wednesday you will have your exam number 3, which is gonna be via Blackboard, of course. So stay tuned so we can give you the instructions on how this is gonna be happening, because we have to make some arrangements in order for make this work. Friday, April 17th, it's gonna be due homework number 12. So just so you know, those are the coming due dates. Very briefly, the techniques to determine concentration and the main goals are to learn how to read and use the burette correctly. This instrument is quite useful for analytical chemistry, so we will be showing you guys how to use it. Next, how to learn how to perform a titration, and then starting from that titration, calculate the molarity of a hydrochloric acid solution of unknown concentration, of course, starting from a known concentration of a solution of sodium hydroxide. And that's basically the idea. That's the reason why you have to do a titration. In this experiment, you will measure the absorbance of light by common fluid dyes in a solution to determine that concentration as well. That's part B of the experiment. And starting from that, you will learn how to perform a Siegel dilution, which is necessary for you to dilute your standard and make your calibration curve, and then learn how to construct and interpret the calibration curves, and to determine the molarities starting from that calibration curve of 3 different dyes in this case, of unknown concentration, of course, starting from their absorbance. So the general information, please go and see all these videos. You have them available in Blackboard. These videos will explain you further how is the experimental procedure to perform a titration and a spectrophotometrical measurement, and before the spectrophotometrical measurement, how to perform a Siegel dilution. So keep that in mind. Briefly, I would like to discuss what's a burette. A burette is a glassware, it's a piece of glassware. In this case, this is a graduated volumetrical equipment that allows you to discharge and measure the amount of volume that you discharge when you are performing a titration. Remember, as I told you, for a titration, you are basically calculating the concentration of an unknown by performing, in this case, an acid-base neutralization. So the base that you are using is a base that has a known concentration, and therefore you can, depending on the amount of volume that you discharge in the end, you will be able to know what's the concentration of your acid. So in addition to that, you always are discharging, so you need to use this little valve over here, plus this tip, which is where you make the final discharge, and you have the burette clamp where you stabilize your burette. And when you are going to read, in this case, your meniscus, remember that the water meniscus, when it's put in any kind of glassware, is gonna always have this curved shape. That's because of the intrinsic properties of water. And remember that you always need to read this looking at the lowest or lower part of the meniscus. That's the right way to do it. So you guys know, keep that in mind. The titration procedure, this is the basic setup. As I mentioned here, you have your burette clamp, you have your burette. Remember that this burette in this case is gonna be loaded with sodium hydroxide. So that's what you have inside of the burette. That's the NaOH solution you have in there. Actually, that doesn't seem too well, so just let me change back again to that color. And NaOH, and the concentration for this NaOH is 1 molar, and then you are titrating, in this case, a mixture of hydrochloric acid of unknown concentration plus the indicator. And that's basically what's going on in there. Now, what's the indicator? Well, the indicator is the one that is gonna allow you to see a change in color when you start adding up the sodium hydroxide to your titration. If you do not put the indicator, you will never be able to see the change in color that is getting described by this cartoon over here. As you can see, in the starting point, you cannot see any kind of change in color whatsoever. However, as you start adding up more volume, more sodium hydroxide volume, you will start looking very light change in color, in pink color, and at some point you will see that that pink color turns out to be constant, remains constant. At that point, that's called the end point or the titration point, and that means that at that point, all the moles of sodium hydroxide that you had have been neutralized also with the hydrochloric acid moles that you are trying to titrate. And that's basically what's going on. If you notice, in this case, we have a 1-to-1 proportion between sodium hydroxide and hydrochloric acid, which means that you will need to add a specific amount of sodium hydroxide, and that's gonna let you know the amount of moles that you have of hydrochloric acid. Moving forward, you will need to watch this video about the titration. This is gonna be really relevant for you guys to understand what's going on, so I encourage you to go and watch this video. Regarding the second part, the spectrophotometrical measurements, remember that when we speak of spectrophotometrical measurements, we are speaking of any kind of compound that absorbs within the visible range of light. That means that it has color that you can appreciate with your eyes. Okay, so any kind of compound that has color, if you do the right and the appropriate approach, you should be able to measure its concentration by a spectrophotometrical approach. And that's what we are trying to do in this case and for this exercise with different colored dyes. Okay, so as I mentioned, the spectrophotometer detects the amount of light transmitted to a solution at a particular wavelength. So you care about the wavelength and the amount of light that is absorbed at that specific wavelength. And that's basically what we will be looking for. If we move forward, this is the basic setup you should have in the experiment if you were to run it, and this is the spectrophotometer. This is the cuvette where you load your analyte, and inside this little hole over here, you will irradiate that sample with visible light within one specific range of wavelengths. Okay? Once you perform according to the Beer law in this case, you will be able to get this absorption over here, and you will be looking for the maximum peak you can get of absorbance, which is gonna be called the lambda max. And that's the wavelength, the specific number of wavelength at which you have always the highest absorption. With those values, starting from a diluted standard solution, you will be able then to have these different points, and once you plot them, because these are just diluted solutions of the same compound, you will be able to make this linear relationship, which is always called the calibration curve. And that calibration curve is going to let you determine the concentration of your unknown. Now, as I told you, you need to dilute your standard solution. What that means? That means that you will start with a stock solution of a dye, and then you will start micropipetting 1000 microliters, and you will start decreasing the concentration of your sample. Therefore, if you start with a 1.6 times 10 to the minus fifth, you will start getting diluted that, and in the end, if you notice, you will get 7.88 times 10 to the minus 7, very diluted solution. And that's the main idea of acid dilution, is just to decrease the concentration of your stock solution until a specific point. That's basically it regarding the laboratory session. Okay guys, so moving forward, now I would like to discuss a few exercises from your recitation guide. Let's start real quick in the exercise number 1. This is going to be related to a titration. So keep in mind that this is going to be really helpful for you. In the laboratory, Matt wants to find out the concentration and molarity of a 25 mL HCl solution using titration. If Matt dispensed 15.4 mL of 1 molarity sodium hydroxide to neutralize the 25 mL he dispensed of hydrochloric acid, what is the molarity of the HCl? Clarification, the HCl was not dispensed. That's the solution you have on the Erlenmeyer flask. Okay, so starting to tackle this question, let's first of all visualize what's going on. So this is my burette, basically, and this is getting loaded with a solution of sodium hydroxide, 1 molar, and I had to dispense 15.4 milliliters of that solution. Now I am transferring that volume to my hydrochloric acid solution plus the indicator, remember, and they are telling me that I have here 25 mils of that HCl, and that's the basic information they are telling me. So in a stepwise manner, remember that first of all you will always need to consider your chemical equation, and that chemical equation needs and should be always balanced. If it is not balanced, remember that this won't work, because at some point you need to consider the stoichiometry of the reaction in order for you to get the calculations done. A few corrections in here. This is not one of the products of this reaction. Don't get confused by that. And this is gonna be the last product you will get in the end from this reaction. Okay, moving forward, the second step is gonna be to determine the moles of sodium hydroxide. The moles of sodium hydroxide can be determined because in this case I have the concentration of sodium hydroxide and I also have the volume I use. If you recall, molarity equals to moles per liter, therefore moles is going to equal molarity times my volume. If I do that, remember that I need to change my volume to liters, and therefore if my molarity equals to 1.0 moles per liter, remember that molarity is the same as saying moles per liter, times 0.054 liters, which is the amount of volume I have of sodium hydroxide. Liters cancels out with liters, and therefore my final result is going to be 0.054 moles of sodium hydroxide. Nice. So now I have my moles of sodium hydroxide. The last step, or the upcoming step, the next step is to determine the moles of hydrochloric acid. And for that I need to consider the ratio between sodium hydroxide and hydrochloric acid. Okay, so if we take a look at the formula I have on top on the first step, that says that I have a 1-to-1 proportion, which means that in 1 mole of sodium hydroxide I have 1 mole of hydrochloric acid. This cancels out, and in the end I know that I have 0.0154 moles of hydrochloric acid. And my final step in this case will be then to take that amount and pass from moles to molarity. If you remember, molarity, and I have it over here, I'm gonna circle it up, is moles over liters. Therefore, you need the volume of hydrochloric acid you had. And guess what? We have it. They are telling us that we had 25 mils of hydrochloric acid. Therefore, this is gonna be used to divide 0.154 moles of hydrochloric acid over that volume passed to liters. So that's gonna be equal to 0.025 liters. And in the end, that's gonna be equal to, let me do this real quick, 0.054 over 0.025.62 molar. And this is it. Now, moving forward, the second exercise is telling me that Matt analyzed a blue dye in a diluted sample of Kool-Aid using a spectrophotometer and got an absorbance value of 0.515. And they are asking me to use my calibration curve below to calculate the concentration of that blue dye. And you can also take a look at the video in this link over here. So let me just underline that. Perfect. And now let's start. If you take a look at the calibration curve they are showing you, you will notice that your y-axis is absorbance, and that's what the data they are giving us. And if you have the absorbance, you have the concentration, because recall that we have a linear proportion between, or a linear relationship, better said, between concentration and absorbance. Therefore, if my absorbance in this case is 0.515, that means that approximately that's gonna fall at this point, right? So if I extend this line throughout the whole axis, I will get that approximately my concentration for that dye, so let's say that this is the dye concentration, is gonna equal to 0.24. I guess that's what it says in the solution area. Anyways, it's really close to that. Molar. Because remember that moles over liters equals to molar. So that should be the concentration you should get in the end. Moving forward, they are asking me to write a balanced chemical equation to complete full ionic equation, identifying spectator ions and writing down the net ionic equation for the following reactions. I will cover up reaction A, you will go over reaction B. So they are telling me that I have a magnesium sulfide this is not yet. Magnesium sulfide plus barium chloride. But if you recall, barium pertains to the family 2A, therefore its charge is always going to be positive 2. Therefore, in this case, I need to have 2 atoms of chlorine per each atom of barium to have a compound and not an ion. Okay? This is going to be a double displacement reaction, which means that in this case, each of the ions is going to pair up with another ion. So you're going to exchange all the ions pairs. So magnesium it's going to be now with chlorine, and barium it's going to be now with sulfur. Now if we take a look at the charges, if you recall, magnesium it's always going to be +2, sulfate is going to be always -2, barium as I mentioned is going to be +2, chlorine -1, and in this case everything remains the same. And now let's take a look at the physical state of each one of the ions I have in this case. If you notice, this reactants, of course, as they are reacting, they need to be in aqueous state, so that's obvious. But now going to the products, if you take a look at the solubility chart, you will notice that chlorines and anything with chlorine ion turns out to be soluble. Therefore, this is going to remain in aqueous state. But now, if you take a look at the table, you will notice that almost all the sulfates are soluble. However, within the exceptions, barium is one of those. Therefore, this is going to be not soluble, and this is going to be then in the solid state. Now they are asking me to complete the full ionic equation, and that just means that I have to break up all my compounds into ions, so I will just express them separately. So this is going to be aqueous state plus sulfate in an aqueous state as well, plus barium in an aqueous state plus 2 times chlorine in an aqueous state, passing to form magnesium in an aqueous state, 2 chlorines in aqueous state, and now here comes the relevant part, because remember that barium is going to be solid and sulfate is going to be solid as well. Now they are asking me about the spectator ions, and remember that the spectator ions are those that never change either its physical state nor their oxidation state in the end. So those that remain unchanged, those are the spectator ions. I will choose in this case cross those who are the spectator ions. Okay, so if you notice magnesium in this case, if you notice from the reactants to the product, is not changing at all. It is keeping its charge and its state, physical state. Now if we notice, with chlorine, the same case happens, because I am keeping the same oxidation state and the same physical state. However, barium is changing from an aqueous state to a solid state, and sulfate is undergoing the same situation. Therefore, that means that these two will be the spectator ions, and those are going to go here. So magnesium plus 2 in the aqueous state plus, or maybe I could just put and chlorine in aqueous state as well. Now about the net ionic equation, what they are asking me to write down are those ions that prevailed, so are those that change in between the reactant to products process. So then there I will write down barium plus 2 in aqueous state plus sulfate minus 2 aqueous state, passing to form in the end barium plus 2 solid plus sulfate 4 minus 2 in solid state. And that's basically what's going on in there. Okay, moving forward. Now they are asking me in this case to, let me see which other one would be relevant. Okay, so number 6, in the following balanced chemical equation, which element is oxidized and which element is getting reduced? That's what they are asking me in this case. So let's go over that. If you recall, this is the reaction. I'm just going to write it down. From the theory, we know that any kind of compound that is in its natural state, it's going to have an oxidation state equal to 0. And in this case, if you notice, zinc and copper, the both of them are in its solid metallic state, which means that they are with a charge of 0. Now, moving forward, if I take a look at the copper chloride solution, if you recall, chlorine always has a charge of -1, and therefore in this case, copper needs to have a charge of +2. And in the other part, the same thing happens. Oops. I don't know how that happened. Okay, here we are. Okay, so minus here, plus 2 here. Okay, now they are asking me which element is getting oxidized and which one is getting reduced. Let's start by oxidation. What's oxidation? Oxidation is nothing more than losing electrons. And reduction is nothing more than winning those. That's basically it. Remember that the electrons cannot just disappear, they need to go somewhere. Therefore, in this case, the element that is getting away those electrons, and those electrons are getting passed to the other element, which is the one that is getting reduced. So moving forward, in this case, if we take a look, zinc is passing to be in a 0 state to be in a +2 state. That means that this is the element that is getting oxidized. So oxidation, in this case, zinc, and which is the element that is getting reduced? If you take a look at it, conversely, copper is passing from a +2 charge to a 0 charge. So it's losing positiveness, right? Therefore, it is getting reduced. So that's basically the answer to that. Moving forward, I would like to discuss these two last exercises and we are good to go. So, arrange the following compounds in order of oxidation number of nitrogen. If you recall, to get the oxidation number, you first of all need to consider, let me write that down, consider the net charge. And when I say that, is that, for example, I will just make one of the exercises and you will go with the rest of them. If I have NO2 and it has a charge of -1, that means that in this case the net charge equals to -1. So all my math needs to go considering that in the end my outcome needs to be equal to -1. Okay? If you recall, oxygen always has a charge of -2. We have seen that a few times before. If I have two atoms of two oxygen atoms and I multiply 2 times -2, that equals to -4. Therefore, what's going to be the charge or the oxidation state for nitrogen? Well, you need to take a number that in the end gets you to a -1 outcome. And in this case, it's quite obvious that that number has to be +3. So the oxidation state for NO2 -1 has to be +3. It is the same exercise for the rest of them with one exception. The only exception in this case is going to be N2. Why? Because remember that N2 is nitrogen in its natural state, and therefore its formal charge is going to equal to 0. Okay? Having said that, I would like to go over this oxidation. They are asking me about the half oxidation, half reaction of this chemical equation here. If we take a look at it, I will just go briefly over this. Lithium, it's in its pure state because it's in solid state, therefore this charge as equals to 0. Chlorine, in this case, once again, is in its molecular form in gaseous state, therefore this has to have net charge equal to 0 as well. And then when I get my final compound, we remember that chlorine always has a -1 charge and lithium always has a +1 charge. So those are the charges I have in the end. Just redo that plus symbol. And that's what I have. So now they are asking me about the half reaction of oxidation. So I need to identify which element is getting, in this case, oxidized. Once again, if you recall, oxidation means lose electrons. Always look at it this way. So in this case, If you notice, lithium is passing to be in a zero net charge to be in a +1 net charge, which means that it is getting oxidized because it is losing one electron. So now let's write that down. I have that 2 lithium moles are passing to form, in this case, 2 lithium +1 plus 2 electrons, and if I simplify that, because I can cancel out all the 2's, lithium in its solid state is going to be equal to lithium plus, plus 1 electron. So that has to be my option C. I hope this helped you guys. I will post these videos as soon as possible. Please email me if you have any questions or if you have any kind of feedback regarding these recordings. Have a good one. Bye bye.